What is up, everybody? We're back. So we're going to pick up right where we left off. We are going to move into question 4. Right here. General matrix multiplication latency. Let's say we want to multiply a weight matrix. Let's say we want to multiply a weight matrix int 8, 16,000, 40,000 by an activation matrix where B is some unknown batch size. Let's say we're on 1 TPU V5E to start. How long will this multiplication take as a function of B? May help to calculate how long it will take to load the arrays from HPM, how long the multiplication will actually take, which is bottlenecking here. Well, okay, so just calculate both. Alright, let's think here. So it should be some ratio of like flops per second divided by accelerated flops per second. And then we need to look at communication bytes divided by HBM bandwidth. No. It should just be like a distance rate equation. So let's see. Let's first calculate how long it will take to load the arrays from HBM. So that should be, let's write this down. How long it will take to load the arrays into HBM. Alright, Oh, from HBM. Whoops. I guess we're not looking at how long it'll take to write from HBM or from our TPU back to HBM. So anyway, first, so we need the number of bytes loaded equals HBM bandwidth times time, right? Distance equals rate times time, yeah. So T is the time. Let's just write that there. Where T is time. Cool. So number of bytes loaded. Number of bytes loaded equals 1,600,384 times 4,096. So this is all 1 byte because we're in integer 8. And we're going to add that to the other matrix, which is B times 4,096. So we can just plug that in, and then HBM bandwidth we can get from this bad boy. So what is it? We're in a V5E. Yeah, V5E. 1 TPU V5E. That is 8.2E11. Okay, so let's plug these in right now. So this at the top. Let's do that math so we can shorten things up a little bit. Well, hopefully it shortens things up. 16,384 times 4,096. That is a big number. Let's just say 6.7 E 1, 2, 3, 4, 5, 6, 7. Wait, is it 8? Bruh. Oh, what am I doing? Should be a logarithm for that. Let's just do 6.7 times 10 to the 8. No, so it's 7. Yeah. Okay, so 6.7 E7 approximately plus 4096B equals, let's go back to our HBM bandwidth, which is 8.2 E11 times T, simple division. T equals 6.7 E7 plus 4096 B divided by 8.2 E11. Okay, so yeah, we have two unknowns, so we can't go any further. Yeah, so this is a function of b. So there's a function. Excuse me. There's a function of b for how long to load the arrays from HBM. Let's say now, how long will it take to multiply? So again, distance rate equation. So this is number of flops. Well, technically not floating point operations. Ops, but okay, number of flops equals, and I want my 5 flops per second per chip for integer 8 equals flops per second int 8 times time. And then again, just plug these numbers in here. So first, just because I have this number, I'm going to plug in flops per second, which is 3.94 E14 times time. And then I just need this value here for number of flops. And so we need to calculate that. So it should just be that same equation as before, where it's like 2b times 2d minus 1 or something. Let me look at my previous notes to see what it was for matrix equation. It's bf times d minus 1. So let me just try to remember what was d and what was f. I think d was the shared size, the shared dimension. Yeah, so you can't see it, but so d is the shared dimension. So it should be 1,603.84 times b times 2 times 4,000 divided by, or minus 1. Let's write okay, so that's gonna be hard to fit in here. 16,384 b times 2 times 4,096 minus 1. Oh shoot. Alright, well, we'll just do this on a new line then. 16,384 b times 2 times 4,096 minus 1 equals 3.94 E14 times T. Scratch this out so the scanner doesn't see it, or at least hopefully it doesn't. Last time I had a lot of issues with the tech translator scanner thing. Had to fix it all manually. But anyway, that should be good. It's not leaking through the page too much. That's good. Alright, we got our equation here. Same exact thing as last time. Well, you know what? Let's distribute this first just to make things a little bit easier. So 2 times this should be 9,192, right? Let's see, 4,096 times 2, 8,192, minus minus 1. There we go. And then that times, oh, whoops, don't forget order of operations. That times 16,384 That's a big number. We're going to shorten that again. Let's do 1.34 times 10 to the e. Let's just make sure that that's the right number times, oh wait, whoops, times 10 to the 8. Okay, that's right. So, which is 1.34 e 8 times b equals 3.94 e14 times t. Again, let's rearrange so we get it in terms of t. T equals 3.94 e14. Ooh. Oops, did it backwards. T equals 1.34 e8 times b divided by 3.94 e14. Okay, so we can very easily verify which is bigger and smaller. So we just have to share these over. So let's go back here. Let's actually distribute this. So 6.7 e to the 7 divided by this denominator. 6.7 times 10 to the 7. Let's say this is all divided by, oh, that should work. 8.2 times 10 to the 11. Okay, which equals 8.17 e negative 5, whatever. Hopefully the AI doesn't pick up that little thing. And then we also want to distribute here, so 4,096 times, divided by, dude, what? Oh, there we go. Divided by 8.2 times 10 to the 11 is 4.99, or we'll just round up to 5, plus 5e negative 9 times b. Okay, so the main thing we're really looking at here is this rate, but because we're going to assume that b is pretty big, let's see what happens here. Let's see. Oh, also, no, I didn't make a mistake here. Yeah, it is interesting that this has like an intercept. So when b equals 0, we have a value, which does not make sense. So is our number of bytes loaded wrong? I think this number here might have needed to be distributed. Yeah. Right? No. That is right. Because the idea is, technically, if our second matrix had a b equal to 0 and it's loading no bytes, we're still loading that number of bytes into memory, which it doesn't really make sense that you would load a matrix into memory if you didn't have a second matrix, but still the math makes sense. Alright, moving on. So let's see here. Let's go back to this equation down here. So let's divide this out now. So that equals, let's do a new equation, 1.34 times 10 to the 8 divided by 3.94 times 10 to the 14, that's a big number, which equals 3.4 e negative 7b. So what we could do is compare these two equations. Oh no, we can't, because these times are not guaranteed to be equal. So let's say this is t bytes. I don't know if you can see that. We're going to label these t's. Let's write t bytes everywhere. T bytes and these subscripts. And then let's make this t here t flops. Where t flops is time to multiply. I bet the LaTeX scanner won't pick that up, but whatever. T flops. Let's go down here. T flops. And we should be good now. So what do we really want to see here? How long will this multiplication take as a function of b? It may help to calculate how long it will take to load the arrays and how long the multiplication will actually take, which is bottlenecking you. So technically it'll take, so let's say total time, let me do this up so I can get some more space. Let's say total time, say t total equals t bytes plus t flops, which equals 8.17 e negative 5, and then let's combine these two together. So what is that number? 3.4 plus, I want to combine it with this number up here, which is the 5e to the negative 9. 5 times 10 to the negative 9. Yeah, so this, the time for the computation dominates, because look, it's barely any different. So plus, whoa, actually, maybe not, because this time is way bigger. So the time to load the first matrix seems like it's really dominating. Well, that depends on how big your matrix is, though. So it's hard to say which is dominating. It depends on your matrix size. But anyway, so if this is more, if B is more than 100, then you start to get the flops matters more than the comms. Anyway, let's write this down. Plus 3.45 e to the negative 7. Whatever. I can fix that manually for the LaTeX scanner. Alright. Which is bottlenecking you? I mean, I want to say for small b, bytes, and for large b, flops. HBM loading is the bottleneck, and for large B, multiplication is bottleneck is the bottleneck. Well, the AI scanner's not going to be able to pick that up. My handwriting, but that's okay. I'll fix it. All right. Now let's do the second part. So what if we wanted to run this operation out of vmem? How long would it take as a function of b? So now instead of HBM bandwidth, There's not really anything saying how fast to load from VMem to the matrix multiplication unit. But it's got to be way faster. Interconnect is not the same. Right? Let's see, is there anything here? That's a tricky one. Let's flip the page over first of all. Say question 4 continued. So how do we know the bandwidth of VMem? Let's scan through this entire document all over again. So maybe this is it. TPUs are very fast. I wonder if there's some of VMem in the appendix. Oh, maybe the question is just saying, like, hey, VMem is so much faster that all we need to worry about is the time it takes to do the flops. That's all I'm guessing is. How long would it take as a function of B? Yeah, I'm literally just going to say, assume that VMem is so fast that we're just, the time it takes is the multiplication time. So, assuming VMem loading is faster, I say much faster than HBM, our time is dominated by multiplication, and thus our total time T total is approximately equal to T, whoops, shoot, let's just write this again, T multiplication, I said flops. Man, I'm making so many errors here. Let's just rewrite this whole thing so maybe the little text scanner will be able to tell. T tot equals T flops. And then we want to say which equals, and then we got to go back here unfortunately. So T flops equals 3.4 e to the negative 7b. 3.4 e negative 7b. Wait, we gotta say approximately. Shoot. Well, whatever. That's good enough. So, alright. Hope y'all can kind of see that. Let's check the answer, see what they say. So let's flip the page back so we can see, we grade ourselves. So the number of operations we need to perform is 2. Where's that 2 coming from? Oh, okay. So they're looking at this first. So we added the -1, which is basically the same thing. Oh, you guys can't see what I'm looking at. So whatever. We added the -1, but same thing. So 2 times 4,096 times 16,000 times B, which is whoa. Why did they get a way different answer for that than me? Oh no, they didn't. Oh, okay. So whoops, I was looking at the bandwidth, the rate. Okay, so they got 1.3 times 10 to the 8. We got the same thing times B. So T math equals 1.3 divided by 3.94. So we get the same thing here. 1.38, 1.3 e to the 8 times B divided by 3.94 to 10 to the 14, which equals I don't think they broke it out. Okay, so we don't break that out, but that's right. Okay, so then for bytes, we need to load. Let's go back up here. We need to load 16,000 times 4,096 plus 4,096 times B bytes to VMem. Bruh. They didn't say how long to load them back into HBM. Whatever. Let's just leave what we have for now. Alright. So we're going to ignore this vector. This means Tcoms equals 6.7, 10 to 7. Yep, so 6.7 E7 plus, they got a way bigger number for B, divided by 8.2 E11 seconds. Assuming as much overlap of communication and computation as possible, the whole multiplication will take the max between those two. Will be flops bound. Well, yeah, so when B is large. Slightly larger than the 240 number we derived in section 1 because we factor in the full impact of D and F. Yeah, I'm not going to change my time or my calculation because I think the wording was a little bit not specific. Anyway, so on to 2. What if we wanted to run this operation out of VMem? Let's flip the page. Oh, whoops. Flip the page here. Let's go back down. I said if we're looking from VMem, okay, yeah, VMem bandwidth, so the MXU is 22 times the HBM. This turns our data loading denominator from 8.211 to 1.8. We got B is greater than 11. Note that in practice we cannot dedicate all of our VMAP bandwidth to loading the weight matrix, so in practice it'll be closer to 20. Alright, I don't know where this got this 22 times. So, whatever. We're just going to leave that. And we are going to move on to question 5. So, let's write this here. Question 5. Interchip interconnect bandwidth. Let's say we have a TPU V5E 4x4 slice. Let's say we want to send an array of type blank to the TPU 00 from TPU 00 to TPU 33. Let's say the per hop latency is 1 microsecond. How soon will the first byte arrive at its destination? How long will the total transfer take? So this should be a pretty simple arithmetic thing. So first, let's draw the 4x4 slice just for better visualization. All right. So TPU 00 and then 33. So let's write all these interconnects here. Bang, 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 bang. We'll ignore all the guys who aren't really connected. And then this should be connected to this. Maybe we can write like that. Right? Or is there a different connection based on what type of TPU it is? I wonder if there's something about the TPU 5EE. along any axis of size 16. No, I don't think that's really relevant. And then also these are connected. But who cares? It doesn't matter. We still need to traverse 1, 2, 3, 4 chips. 1, 2, 3, 4. Yeah. To hop from 0, 0 to 3, 3, we need to make, was it 4 hops? 1, 2, 3, 4. Yeah. 4 total hops. Thus, oh, interesting. So it's different between how long will the first byte arrive at the destination, how long will the total transfer take. So per hop latency is 1 microsecond. I need to think about this for a little bit. So they're trying to say each byte takes 4 microseconds. I mean, that's the only other way I can see solving this. So let's make that assumption. I'm going to flip the page so y'all can see better and I have more room. Say question 5 continued. Each byte takes 1 microsecond per hop and does 4 hops. Therefore, the first byte arrives in 4 microseconds and the total transfer equals 4 microseconds times the total number of bytes. So for BF16, it's 2 bytes per. Let's just write times total bytes. Let's say equals 4 times 2 times, and the matrix. 8 times 128 times 8,192. Let's do that calculation. 4 times 2 times 128 times 8,192 is 8.4 e to the 6, right? 10 to the 6. Yeah. Which equals 8.4 e to the 6, e6. Microseconds. Which equals, what's the conversion of microseconds to seconds? It's probably just 1, right? So it's probably 8.4 seconds. Cross seconds to seconds. Let's say it's 8 million. Yeah, it's 8 seconds, which equals 8.4 seconds. All right, let's see how good we did. So let's go back to the first page, see the first part. And then also what I'm going to do is highlight 4 transfers just to So, so y'all can't see. Highlight 4 transfers just so that's easier to visualize what's going on. Well, that might be a mistake depending on what the answer ends up being. Alright, got 2D connectivity because we only have a 4x4 slice with no axes of size 16. We have no wraparound connections. Oh, okay, well, whoopsies, my drawing's wrong. Thus, there are 2 ports from which our target chip can receive data, likewise 2 ports from which our source chip can send data. The amount of data we have to transfer is 2 times 8 times 128, yeah, so that's this side. Did I get that right then? Oh, I didn't even do that calculation. Well, let's see where they go with this. It's how many bytes? I think we did that same calculation 2 times in the matrix. We can transfer from both ports simultaneously, set half the array right and half down. Oh, what? Okay, so I did this wrong. Which means it'll take about 1.7 e to the 7 divided by 9 e to the 10 equals 188 microseconds to transfer the whole array through, assuming we're bandwidth bound. In a 4x4 slice, we have 6 hops between chips. What? Chips 0, 0, and 3, since there are no wraparound links for axes with fewer than 16 chips. Since the latency of each hop is 1 microsecond, first byte, or I don't know, 6 microseconds, the total transfer will take about that many seconds. Yeah, I'm very confused, I'm not gonna lie. Why would you add 6 microseconds to 188? Since the last byte must likewise traverse the 6 hops after it leaves the source. In general, the latency and bandwidth terms are additive, though here the latency is a small correction. So saying latency and bandwidth are different, that's the issue. So I guess I thought of this question completely wrong. I'm going to need to sit and think about this for a little bit. So what does it mean that there's only 2 ports that can send data from and that can receive from? I don't know exactly what that means. Yeah, I didn't read close enough. Why can't you just traverse from one chip to the next, down, down? 1, 2, 3, 4. 1, 2, 3, 4. Does it have something to do with this? Does it have something to do with the fact that no, they're not doing a wraparound and then a wraparound? No, that wouldn't make any sense. Let's go back to this answer here. So this first part is throwing me as well. So there are 2 ports from which our target chip can receive data. Likewise, 2 ports from which our source chip can send data. Oh, okay, so yeah, that's obvious. So So I can send and receive data through this port and this port. Bang, bang. And this can receive and send from this port and this port. So there's two ways to do this. Well, technically, there should be many more. But then you'd have to have logic for like splitting it at these nodes. So anyway, so we got bang, 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 bang. Okay, so 2 ports means that we can split it up. The amount of data we have to transfer is that. Yep, we can transfer from both ports simultaneously. Yep, send half right and half down. So half right, half down. So where's the 4.5 E10 coming from? Is that from here? Yeah. Whoopsies, did that wrong. Alright, whatever. Should have known from ICI bandwidth in a literal question. That's what they were talking about. But anyway, metadata. Okay, yep. Per second, which means it'll take about that many seconds to transfer the whole array through, assuming we're bandwidth bound, and a 4x4 slice. Wait, before I go on, I'm curious now about the latency. I wonder what causes that latency. But you know what? It all makes sense now. So there's latency. This doesn't make sense why it's additive. So there's latency, and then it takes the bandwidth time to actually transfer. Yeah, so this actually makes complete sense. Now 4x4 slice, we have 6 hops between chips. Okay, actually that still does not make sense. Why are there 6 hops between 3? Oh, 0, 0. Oh, I'm indexing wrong. This is 0, 0. This is 1, 1. This is 2, 2. This is 3. Oh, whoops. 0, 1, 0, 2, 0, 3. This is 3. No. This is 3, 3 right here. This bad guy. Bad boy. So what I'm going to do is scrap this entire page and rewrite it. So let's just X this out so I can remember. Don't. Oh, shoot. I just X'd out question 4 as well. That's right. Question 4 is good. I'm going to have to scan it to Tech right after this so I can remember all these mistakes that I made here. Let's flip over. Question 5 over here is wrong as well. I must say, need to rewrite question 5. And I should remember that. Anyway, let's do the hard question now. Pulling it all together. Question 6. But before I do that, I'm going to take a quick break since we've been going for 43 minutes with no end. I will catch y'all in a little bit. Alright, we are back. Question 6. Imagine you have a big matrix A, integer 8, sharded evenly across TPU V5E 4x4 slice, but offloaded to host DRAM on each chip. Let's say you want to copy the entire array to TPU 00 and multiply by a factor of that. How long will this take? Oh Lord. Okay, yeah, that's just the next section. Alright, let's go back. All About TPUs. Oh, these are. Oh, this appendix looks very cool, actually. Let's stop getting distracted, though. Alright. Question 6. Imagine you have a big matrix A, sharded evenly across a TPU V5E. 4x4 slice, but offloaded to host DRAM on each chip. So you want to copy the entire array to TPU00 and multiply it by a factor, BF16, 8. So you're not really doing any interchip interconnect, right? It looks like you need the time to go from DRAM to HBM and HBM to one chip, and then the amount of time to multiply this vector by this matrix A. So let's write that down. We'll see if this is hypothesis is right first. So time equals time DRAM to HBM plus time HBM to VMEM plus, I mean, do we even really have to consider the time from VMEM to matrix multiplication unit? Which one was it? 4? So yeah, let's just do it. Plus VMEM to matrix multiply unit. Well, I hope it's a matrix multiply unit. It's not the vector one. But whatever. The same idea. Plus time multiplication. Alright, let's do all of these bad boys. So first time from the DRAM to HBM. Let's see if they have that somewhere. So it should be DCN, right? Where's a PCIe? No, it should be PCIe. It's between a CPU host and its associated trays of chips. Right. I'm going to assume it's PCIe. But I just don't know where to get that number. So there's not really a number for this somewhere, but I mean, we could take this number probably for the TPU v4, just assume it's the same. Oh, there we go. PCIe bandwidth. So what are we on a TPU V5E? Let's just say, assuming PCIe bandwidth of 1.6 E10 bytes per second. Time DRAM to HBM equals 1.6 E10. Wait. Should be a distance rate equation. So number of bytes equals that times time. So if you want to get time, you got to divide by this. So that's in the denominator. Equals number of bytes loaded. Oh shit. So we got to break it up into what's loaded and what's written probably. How long was it? Let's just do the bytes loaded and in bytes written all together because it's still the same backwards. Plus backwards up top here. Okay, number of bytes loaded slash written divided by 0.6 E10 bytes per second. That gets us seconds. Wow, this question is going to take a long time, but that's all good. So, number bytes loaded equals I wonder why they wrote it like that, 128 times 124. But it's also sharded evenly, but offloaded to host DRAM on each chip. So I think that just means that we can basically use this number instead of this number times the number of chips we have. The fact that they use the word but makes me think maybe not. It's bytes per second per chip times chips. Let's just write that down. Number of bytes loaded is, yeah, why is it written like that? Well, anyway, so if it's sharded evenly, we can divide each of these by 16. So this is 128 times 124 divided by 16 times 128 times 1024 divided by 16. I wonder why they're writing it like that. Why are they writing that time symbol there? Whatever. So let's do this calculation. We only have to do it once and then square it. So 128 times 1024 divided by 16, and then take this answer squared. 6.7 e to the, what is that, 8? 6.7 times 10 to the 8. That was to the 7. Gotcha. Alright. Which equals 6.7 E7 bytes loaded, number of bytes written. Oh shoot, that's just from A. Plus, what about from the vector? Problem is, you're gonna have to duplicate because you don't have enough in your batch size. So let's just say, well, we have to write that down. Let's get rid of this. Bytes loaded from matrix. Number bytes loaded from vector equals one times 128 times 124, 1024 divided by 16, where first factor is 1 because we cannot shard batch size to less than 1. Diagram. Let's visually check this so that we're not being dumb here. Whoops, whatever. We'll have a little trapezoid there. This might be the best drawing I've ever made. So yeah, I also think I did this completely wrong. I think you have to divide it by 4. Yeah. Whoopsies. Until I'm getting tired. 4, 4. How many bytes are actually loaded here? Let's go back to this thing. Let's change this to 4. It's actually 1.07 times 10. Point 07 E. Not whoa. Oh yeah, way more bytes loaded. Wait a second. That's per chip, right? Per chip. Yeah. Bytes loaded from matrix per chip. Bytes loaded from vector per chip. And this is divided by 4. This is 2 because we can divide by 4. Get rid of this bad boy. I'm gonna skip the diagram for now. Man, pen was probably a bad idea. Question 6. Continued. Let's go back. So number bytes loaded from vector per chip equals 2. So it's 128 times 1024 divided by 2 because we have that other factor of 2 and this is really divided by 4. Cancel out. So we get 65,000 equals 65,536 bytes per chip. Hope these numbers are right. Oh, it's times 2 because it's BF16. Man, making a lot of mistakes here. A lot of scratching out. So that's wrong. Really have 130,000, maybe a little bit more, 131,000 times 2. 131,000. 31,072 bytes per chip. You know what? It's late. It's 9:32. I've got to be in the fab by 7 a.m. tomorrow, which means I should be going to bed here soon. So we're going to take a break here. We are going to pick back up tomorrow. Until then, catch y'all later. Bye-bye.